Alright, this is Math 1, Section 5.4. We're going to talk about medians and altitudes, and then the point of concurrency that both of those make. The first thing we're going to talk about is medians. This is Section 5.4. We'll talk about the median. The median, the definition of a median, read it right there for me, Nash. The median of a triangle, nice and loud.
The median of a triangle is a segment from a vertex to the midpoint of the opposite side.
So it goes from the vertex to the midpoint of the opposite side. That is a median. It can or cannot be a perpendicular angle right there. It might or might not be. Okay? I'll try to stand out here. So the median goes from a vertex to the midpoint of the opposite side. That means that if this amounts 4, this amounts 4. It's pretty easy. It cuts the opposite side in half. Okay? The median from here to here, and then this would have to be equal to this. Okay? How many more medians do we have? One more. So we go from the vertex through there to this, and that is equal to that. Okay? 3 points, three slashes, 3 slashes. Okay? The centroid is the point of concurrency that the 3 medians make. The 3 medians create a point of concurrency called the centroid. The centroid has 2 special properties. The first special property is that it is always on the inside. What other point of concurrency is always on the inside? Very good. That was a review question. So the centroid and the incenter are always on the inside of the triangle. Whether it's acute, whether it's a right triangle, whether it is obtuse. It's always on the inside of the triangle. Okay, that's its first special property. Yep.
So the medians are almost like the perpendicular, but I said you said they're not perpendicular.
That's right. That's right. They're not perpendicular. Exactly right. The second special properties comes from this theorem 5.8. We're looking on page 278. It says the medians of a triangle intersect at a point that is 2/3 of the distance from each vertex to the midpoint of the opposite side. The centroid has a special property, and I call it the 1/3, 2/3 property. I know you don't know what that means yet, but once I explain it to you, you'll understand what the 1/3, 2/3 special property is. Okay? And this is it. If I take a centroid, okay, I'm telling you that this is the centroid, point C here. It always cuts this total distance. If this is A and this is B, and that's a median, that's the whole distance, it cuts it in thirds. If I have a circle like this and I cut it up in thirds, right, then I've got a third of the pizza right here. Okay? The centroid cuts up this into thirds. This bottom piece down here, the shorter one, the one with the side, is always a third of the total distance. That's where the 1/3 comes in. The side containing the vertex, look in your theorem, 2/3 of the distance from each vertex to the midpoint of the opposite. This side containing the vertex is always the 2/3 side. The centroid cuts each median into 1/3 and 2/3. That is a special property. It's unlike any of the others. Right? The circumcenter is equal distance to the vertices. The incenter is equal distance to the sides. The centroid is always on the inside, and it has this special 1/3, 2/3 property. Okay? So going back to the triangle, with this one here, would it be 1/3 or would it be 2/3? It'd be 2/3. Why? Because it's this part that has the vertex. right? It's the longer. Look how much longer it is than this one. And I know this is my hand-drawn graph, but you get the idea. This is 2/3. This is always what? 1/3. So this is 2/3, and this is 1/3. All right, let's finish it out. This one here, this median here. This part here has to be what? 1/3 or 2/3? This one here.
1/3.
Why is it shorter? Why is it 1/3? Because it doesn't have the vertex, or you could say because it has the side. Right? It's the shorter one. If that one's 1/3, then how much is this one down here?
2/3.
2/3. All right. An aside question: how far is it all the way around the circle? How many degrees all the way around the circle?
360.
360. So what would each one of these angles have to be? If they were equal,
Like 33.3.
and they added up to 360, they would have to be how much?
Something.
120, 120, and 120. Okay, all three would have to be 120.
What do you call it that we're learning, like the centroid?
This is the centroid. They're called points of concurrency. That's the generic term. Okay? All right, so how are we going to get a problem out of this? All right? Let's look at a problem with the 1/3, 2/3 property. It's going to be that easy. They're going to tell you that point C is the centroid, okay? Or they may just do this and show you that it cuts all three sides, that you have three medians, okay? They may not tell you that point C is the centroid. You may have to figure it out. But if this shorter part equals 1/3, then how much is X going to be if it's 2/3? Double the amount. How much is X going to be?
8.
8. X is equal to 8. Was that easy?
Yeah.
Yeah. X is equal to 8. You just double the amount. All right? What if they give you the longer one? What if they tell you that that part's 18 and they say find Y? What would you have to do there?
Divide by 2.
Half. Can you handle that?
Yes.
I hope so. Okay? 1/3, 2/3 is very straightforward. Okay? What if they did this and they told you AB, the total of AB is equal to 36? Could you figure that amount out?
Yes.
If this shorter part is X, then how much is the longer part? 2X. It's always double the amount. So this amount would be 2X, right? The total of X and 2X, if we add those together, what does that equal? 3X. So 3X is equal to 36. What is X equal?
12.
X equals 12. Could you have figured that out a different way? Sure you could have, right? You could have divided 36 by 3 and said X equals 12 right off the bat. Okay? But that's about as hard as they're going to get. All right? Questions on the 1/3, 2/3 special property? Okay? All right, what's the other one we got to learn? Which is made up of the altitudes, right? How are we going to remember that? What's our little saying? What's our saying for centroid? I didn't talk about it. It's in your little chart here. Here we go. Centers of triangles. Let's come up here. What was the first one that we learned?
PVC.
PVC, right? Perpendicular bisectors intersect at a point called the circumcenter. All right? So then we learned, well, this is the one we're going to learn just right now. That's not it.
What if he wants me to turn?
How about that? That's the one we just learned. Med-Sen. Write that down. MEDCEN. The Med-Sen. The Med-Sen means that the medians make the centroid. The medians make the centroid. Look, the shorter side is how much? 8. The longer part is how much? 16. And what's the total?
24.
24. So there's an example of what we're talking about. If you come on down to the chart that has it all in there, look at there. It doesn't have the 1/3, 2/3. She left that part out, but that's okay. Centroid, the med-cent is made up of the medians, and it's always on the inside. What you would write right here when you print this out is the 1/3, 2/3 special property. I can write it right now. 1/3, 2/3 property. Okay. All right. So the last thing we have to do is talk about the altitude. What is altitude? If you talk about a mountain, what is altitude?
How high it is, or how high
Very
up you
good.
are.
Altitude is another word for height. The height of the triangle can be measured by the altitude. The altitude, the definition, if we come over here to the definition, the definition of the altitude is that it is a perpendicular segment from a vertex to the opposite side. Okay? So the altitude is from the vertex to the opposite side, and it's a right angle. So this is the altitude. If I have the three altitudes, like that, right, these being altitudes, then there is the point of concurrency, and it's called the orthocenter. The way you remember that is A or. In our little chart there it says A or, like that. The altitudes make the orthocenter. Let me do a different triangle. I think some of you are confused.
Yes. That one just looks weird.
Well, it does, and it's on the triangle. It's right there. But if I make it like this, and this, and this, and this, then people see it a little better, right? If it's an acute triangle, then where is it? On the inside. If it is a right triangle, where is it? On it, not on the hypotenuse. It's on the vertex this time. And if it is obtuse, where is it? Outside. So it's in, on, or outside the triangle. And the good news is, that's it. There's no special properties. There's no real problems from it, other than maybe some right triangle type problem, Pythagorean theorem type problem. But we say it is a bore. Why is it a bore? Boring because there are no special properties. Write that down. No, other than where it lies, in, on, or outside, there are no special properties.
For the orthocenter?
For the orthocenter, that's right. The orthocenter is made up of the what? Altitudes. The altitudes make the orthocenter. What makes the centroid? The medians. You got some studying to do, right? What makes the in-center? Abby. What makes the in-center? Abby, Abby, Abby. The angle bisectors, that's how we remember it. A, B, I, Abby. The angle bisectors make the what? The in-center. They make the in-center. And then PCB, the, whoops, PBC, perpendicular bisectors make the what? Circumcenter. Okay, please don't talk. Yep.
Will the orthocenter ever, is it not like the centroid because it doesn't have the...
It does not have the 1/3, 2/3 property.
Okay.
It does not. Anybody else have a question?
Similar to the last lesson we learned.
How so?